Good evening everyone. Today let us see the introduction for chapter 1, relations and functions, from class 12 mathematics. Before we begin with the things related to class 12, you need to remember and recall what is a relation that you have studied in class 11. Let's see what is it. Relation. A relation are defined from A to B, defined from A to B is nothing but a subset of Cartesian product A cross B. How do we symbolically write this? Let's say relation from set A to B is nothing but subset of A cross B. Supposing if the relation is from B to A, we write it is subset of B cross A. Do we always need two sets to define a relation? Definitely not. So let's see the next point. A relation are defined on A. This time I am not saying from A to another set. I have just mentioned on A. What is this? Is nothing but a subset of the Cartesian product A cross A itself. We don't need two sets to define a relation always. It's enough if the relation is defined on a single set, then we say that it's a subset of the Cartesian product of its own set. How do we symbolically write this as? R from A to A. This implies R is subset of A cross A. Next, how many relation we can define? A very important one mark, number of relations. If the relation is from A to B, then supposing number of elements in set A is B, number of elements in set B is Q, then how many relations will be there? Number of relations will be 2 raised to PQ. If it is a relation from A to A itself, having number of elements in set A as P, then how do we write number of relations? Number of relations will be 2 raised to P into P, or 2 raised to P square. A very important results these two are. Please note it. Let's see one example of relation. Set A is 1, 2, 3, 4 and relation R is defined on A such that, what is the relationship between the elements? Such that R is equal to the ordered pairs x comma y and x plus y equal to 5 followed by xy belongs to set A. This clearly indicates that the relation is defined on A. Though already it is mentioned, sometimes it is specially given in the question. Okay. Now let's see what are the elements that come under relation. I would suggest that first let's go the pictorial representation or arrow diagram representation. We have set A, again set A only because the relation is defined from A to A. 1, 2, 3, 4. 1, 2, 3, 4. The relation is now from this set to this set, and check which are the ordered pair is satisfying. I'm just taking randomly one pair 1, 2. Whether this 1, 2 satisfies all of these conditions? Definitely not. The first condition itself, x plus y should be equal to 5. When I take 1, 2, 1 plus 2 is 3, which is not equal to 5, so it is not satisfying. So which are the ordered pair satisfying? With 1, not 1, 2, 3. Anything with these three elements will not satisfy. So I am checking this 1, 4. Yes, it satisfies. With 2, same way, 2 comma 3. With 3, 3 comma 2. With 4, again 4 comma 1. So this is the arrow representation of the given relation. Now let me write in roster form. The relation is no particular order. You can write the ordered pairs in any ways. We have totally 4 pairs. 1 with 4, 2 with 3, 3 with 2, 4 with 1. So this is the relation. This is all about recall class 11. Hope you are now clear about relation. Now let's see what is the first point in class 12. The first definition is empty relation. Empty relation. The name itself clearly tells that in relation there are no elements. It's empty. So let's see the definition as well as an example. A relation R defined on A is called an empty relation. Is called an empty relation if R is equal to null set. There are no elements satisfying. Let me give the same example that I have taken just before. Set A is 1, 2, 3, 4. I am defining relation alone in a different way. X comma y, x plus y equal to 100. Both x, y belongs to set A. Check with this mapping if you are trying. 1, 2, 3, 4, 1, 2, 3, 4. Whichever the pair you check, none of the pair will satisfy the condition as x plus y equal to 100. So how many elements are output here? Nothing. So it is called an empty relation. How do we denote an empty relation? With this symbol called phi. So this is the first definition you have in class 12, which is empty relation. Hope it is clear. The next definition is universal relation. Universal relation. Again, by the name, I think you can make out this relation contains all the elements of the Cartesian product. Okay, a relation R defined on A is called as a universal relation if R is equal to the entire cross product A cross A. Let me take again the same example with less number of elements. Let's say this time I have only 2, 3, 4, whatever it is. I reduced one element. X comma y. This time I am taking x plus y is not equal to 100. X comma y belongs to A. Try with this mapping procedure. If I said 2, 3, 4, 2, 3, 4, you try with 2, 2, 2, 3, 2, 4. What is the condition I have given? Sum is not equal to 100 and both elements should be from A itself. So I can clearly say that all the pairs 2 with 2, 2 with 3, 2 with 4, similarly starting with 3, 2, 3, 3, 3 with 4, same way 4, 2, 4, 3, 4, 4. Yes, if you see that my relation is exactly matching with the entire cross product of A cross A, so we can say it as universal relation. This is the example for universal relation. And definition 3 contains 3 subparts. Very, very, very important. Definition 3. relation R defined on set A is called, there are three subparts, is called, number one is reflexive. When do you say the relation is reflexive? For all, hope you know this symbol, it's called for every. For all A belongs to set A, we should have, or implies, we should have A comma A in the relation. It's suppose the previous example, if you see, I have taken set A with 3 elements. So for each of the element, first element was 2, so you should have 2 comma 2. Second element was 3, 3, 3. Third element was 4, so 4, 4. So if you have A comma A in R for every element of set A, then we say the relation is reflexive. Next, symmetric. If you have a pair A comma B in relation, implies you should also have B comma A as well in relation. Remember, if you have a AB in relation, then only look for BA if it is in relation. For all, again, for all, where will you take the elements from? All these elements should be from given set A. Next, third subdivision is transitive relation. When do we say a relation is transitive? If there are pairs A comma B in relation followed by B comma C is in relation, then you look for A comma C is also in relation. Something you have to look here. The first one is A comma B, second one is B comma C. Is there any connection? Look, here the output is B, here the input is B. So remember to take such pairs only. If you have A comma B in relation followed by B comma C in relation, then look for A comma C, is it also in relation? If you find that this is satisfying, then we say that the relation is transitive. Again, from where do you take these elements? A, B, C, all these are from given set A. So this is definition 3. With an example, we will see what is this relation, okay, followed by another definition, then I'll give an example. Final definition in relation: an equivalence relation, a relation R defined on set A is called an equivalence relation. An equivalence relation if R is reflexive, whatever we have seen in the definition 3, these 3, reflexive, symmetric, transitive. If the relation is reflexive, symmetric and transitive, all the 3 are must, symmetric and transitive. A relation which satisfies all the 3 conditions, we call it with the special name as it's an equivalence relation. This is all about the definitions that you study in relations and function and relation. What we have seen is just a relation. Let's see an example whether the given relation is an equivalence relation or not. Okay, with an example, let A is equal to, or else let R defined on set of integers Z given by, What condition the relation must satisfy? Let's see what they have given. X comma y, the relation is x minus y is divisible by 2. Okay, hope this too is clear. Divisible by 2. This is z set of integers, so this is the condition. And they have clearly mentioned that relation is defined on set of integers. So whatever you take must be an integer, do not take non-integer. Now what is the question? Check if R is an equivalence relation or not. If R is an equivalence relation or not. How do we approach? To say a relation is equivalence, all the three definitions must be satisfied. Suppose when you do, you feel that symmetric case has failed, then no need to proceed with any other case. You can just say that one of the definition is not satisfied, hence it cannot be an equivalence relation. Okay, and there is no particular order you need to follow. However, following in the same manner, reflexive, symmetric, transitive will add to the more clarity, so try to follow that. Let me see. First, what is the first relation you have? Reflexive. How to do it? Let's take an integer. Let's say a belongs to an integer. Why we take some random variable? Because we cannot check for each and every integers. That's not humanly possible. There are infinite elements in the set of integers. We cannot verify for each integer whether the given condition satisfies or not. So we have to give the generalized explanation or valid reason to say or to deny the relation is true or false. I am taking an integer a belongs to z. For any number value, for any value a, do you agree that a minus a is equal to 0? And I am writing it as a minus a equal to 2 times of 0. If you are able to write 2 times of an integer, which means it is divisible by 2. So I got it. Look, what is the relation? If x minus y is divisible by 2, then xy is in relation. I have here a minus a is divisible by 2. So then which pair is in relation? From this I understand that a comma a satisfies the given condition, therefore a comma a is in relation. It is true for all the values. Okay, so R is reflexive. R is reflexive. Now let's see the second thing, symmetric. Again, I'm taking two different elements. A, B belongs to set of integers. And what is symmetric definition? I have given here just before. Look, if you are having the pair A comma B in relation, then look for whether B comma A is also in relation or not. Let's see. According to the relation, we should have already A comma B is in relation is true. Assume like that. It's true, which means it has satisfied the condition that is given in relation. What is the condition? A minus B is divisible by 2. This is using words. So mathematically, can I write a minus b is 2 times of some integer, let's say x. X is an integer. Even if it is divisible by 2, I can write 2 times of some integer. If a minus b is 2x, what do you say about b minus a? Is b minus a is negative 2x? I can also write b minus a as 2 times negative x. Whenever I am able to write 2 times of an integer, it clearly tells that it is divisible by 2. So b minus a is also divisible by 2. So I find a pair b comma a is relation. You remember the definition? If there was AB in relation and you get BA also in relation, then we say that R is symmetric relation. Finally, transitive. Let three elements, three integers I am taking. What is transitive says? If AB in relation followed by BC also should be in relation. So AB in relation and BC in relation means they have already satisfied all the conditions that are needed for relation. So A minus B is divisible by 2, as well B minus C is divisible by 2. These are sentences. Let me put mathematically. A minus B is divisible by 2 means, let's say 2 times of M. Let me mark it as equation 1. And B minus C is also divisible by 2. Let me say 2 times of N. And I need to find the relationship between the elements A and C with the help of these two true facts. So what am I going to do? Add both of these equations. Adding both, see what do you get. A minus B added with B minus C, 2 times M added with 2 times N. Here B gets cancelled. You get A minus C is equal to 2 times of M plus N. Please note again I am able to write 2 times. What do you mean by 2 times of some integers? Which means A minus C is also divisible by 2. So I will get A comma C pair in relation. Again, recall the definition. If AB, BC, then we say R is transitive. Hope you remember what this relation is, equivalence or not. I get all the all the three parts: reflexive, symmetric, transitive. All the three are true, hence the relation R is an equivalence relation. We have seen an example where it is an equivalence relation. With one more example, you will understand that like which case is failing. Is it necessary that a relation is always an equivalence relation? Definitely not. Okay, I'm going to justify that. Let R defined on set of integers. This time let's take for a change set of real numbers such that R is equal to x comma y is in relation if x less than or equal to y, and as usual xy belongs to real numbers because the relation is defined on real numbers. Do not expect this condition always mentioned, because already in the question it is given that on set of real numbers, so they don't even mention this. In that case, don't get confusion because it is already given in question. So let's check if R is reflexive, symmetric or transitive. This time I am not asking it as is it equivalence or not, because purposely one of the case is going to fail or something like that. So I know it is not an equivalence relation. That's why we are checking if the relation is reflexive, symmetric or transitive. And then finally let's conclude about equivalence relation. Though they didn't ask, just writing an additional point. Okay, let me check for reflexive. Let A belongs to a real number. For any value A, Do you agree that A will be equal to A is true every time? Yes, a number is equal to its own number. What is the relationship here given? Look here. If x is less than or equal to y, how to read this? X is less than or equal to y. Yes, I got here A is less than or equal to A is true, because I already got A equal to A. So, A pair is seen in relation. R is reflexive. Now, let's see for symmetric. Let A be two real numbers. I'm going to take two specific examples because symmetric case is not necessarily true here. If A equal to 2, B equal to 7, you can take any example. I just took on my convenience, that's it. If, check, if A comma B is in relation, yes, 2 is less than or equal to 7. This implies 2 comma 7 is seen in relation. But what about the reverse fact? 7 less than or equal to 2 is false. It's not true. Implies 7 comma 2 is not in relation, or I can say B comma A is not in relation. Therefore, R is not symmetric. Transitive next. I'm taking three numbers. A, B, C belongs to real numbers, and as per this relation, AB is in relation as well BC in relation. What is meant by AB in relation? It has satisfied the condition that is mentioned in relation. What is the condition? That is, A is less than or equal to B is true. Also, BC is in relation. So what is meant by that? B is also less than or equal to C. This is the second inequality. Hope you know to compare the inequality. We are saying that A is lesser than or equal to B and B is less than or equal to C. So, when I compare all the three numbers A, B, C, hope you understood that A is the smallest number, C is the biggest number, then obviously A is lesser than or equal to B followed by B lesser than or equal to C is true. But we need condition between A and C. So from this I can write A is less than or equal to C, which is true. Therefore, I get N. Therefore, R is transitive. Equivalence. Is it true? Because symmetric case is not true. Hence, R is reflexive and transitive, but not symmetric. Hope the session was fruitful to you. In the next class, we will see some important questions, board exam point of view questions from relations topic. See you again. Thank you all.